Let's start with where we left off. I talked about the three areas of points of contact and conflict. Then I said we are going to build a new approach to combining the principles of quantum theory and gravity based on this. So, the first one was something which we had already expressed. I am just reminding you of that gravity should not break this symmetry. So, the gravitational dynamics has to be invariant under this shift. This is the kind of a postulate which we are taking in order to approach toward dynamics. I also pointed out that we do not have a good general principle for studying dynamics, and this would serve as that general principle. So, once you have got that, so this is again reminding you that matter equations of motion remain invariant when a constant is added. So, I elevate it to the status of a symmetry, and I claim that gravity must respect this symmetry. This tells you that the way this TAB is going to appear is very different from the way it appears in the conventional theories. In particular, I had already told you that if you want a generally covariant theory based on a local variational principle, you cannot vary metric as a dynamical variable, which tells me that TAB has to be put in by hand because it is not going to come out of variation of the metric. So, the entire principle is going to be different from what one is usually accustomed to in general theory of relativity. So, how can I have a TAB such that TAB plus a constant into Kronecker delta AB does not change anything? Is there a combination of TAB which remains invariant? The simplest combination you can think of is TAB dotted with two null vectors. So, TAB, if I go and add to it a quantity which is proportional to GAB or up and down Kronecker delta AB, then LA, LB contracting on it will give me L square, and if L is a null vector, then this quantity is 0. So, the matter sector should be represented minimally by a combination like TAB, LA, LB with some null vectors coming. And that null vectors obviously brings you ideas like a null horizon or a null surface which is acting as a horizon for some observers, etc. So, here is a and this also has a simple physical meaning. I will show it to you in a minute. I mean, all this is, first I am going to take one rapid pass and then I am going to come back and discuss in detail. This has the interpretation as a heat density contributed by matter on the null surfaces. The more precisely, if you take a local Rindler horizon, this is something which we have described just to remind you, take any arbitrary space-time, take an arbitrary event, take the null line going through that, take a congruence that defines for you a null surface. You can construct a Rindler observer who is very, very close to this null surface, who sees this null surface as a Rindler horizon, who attributes to it a temperature. But there is matter all over, and he will also see this matter crossing this. And in fact, as long as he is straddling along the null surface, it will take infinite time for matter to cross it. It is like chucking some matter into black hole horizon. It will cross the event horizon only at your infinity. But of course, here it is all local, so there is some length and time scale set by the background curvature, but still asymptotically it will approach that, but it is going to do this. And that crossing matter carries along with it an energy TAB, and one can show, this is why I said this is more in the spirit of a colloquium, that I am not going to prove to you that this TAB LA LB has the interpretation as the amount of heat energy per unit area per unit affine time. It is like time. So, you can think of it as per unit area per time. There is no natural time defined for the null surfaces. Instead, you have something called an affine parameter for the null congruence. So, this quantity has a nice interpretation, and that fixes your matter sector. Now, you want to bring this into a extremum principle. The most natural choice again is that since this is the heat density of the matter, the heat density contributed by matter crossing a null surface, you have to add apples to apples. So, you have to have some kind of an expression for heat density of the gravity. Now, heat densities are temperature times entropy density, and the entropy densities are the number of degrees of freedom per unit area is what is going to determine the entropy density. So, these are coming out of some kind of a degrees of freedom, microscopic degrees of freedom, and you need to know what this is, which we do not know yet. So, if you have this combination, and then you can think of this as heat density integrated over some volume is like entropy, okay, and that is should be something like the logarithm of the total number of degrees of freedom a la Boltzmann, and this is the quantity which you are maximizing. Either you can think of maximizing S or you are thinking of maximizing this omega total. So, how does it go? Let me try to explain this in slightly greater detail. So, suppose there is certain number of degrees of freedom, which I denote by rho g for gravity, which is going to depend on various geometrical quantities. Gn is n goes 1, 2, 3, etc., like RAB, okay, which will be a geometric quantity in the coarse grained description. It can also depend on some intrinsic variables which are relics of the pre-geometric or quantum gravitational or microscopic structure. We will see how it concretely gets realized. Then you multiply it by the number of degrees of freedom of matter, which will of course depend on its TAB, and it can also depend on these degrees of freedom with which it is talking to, and it can also depend on geometrical variables. I have not indicated that. So, you immediately can write this. This phi a turns out to be a fluctuating null vector field. So, if you think of that as null vector field, then you have product over null vector field, and this product you think of it as exponential sum of this quantity, and this is what you are going to write as the heat density of geometry and heat density of matter, which is what you are going to expect. Just to give you a preview, when you do everything right, you find that the heat density of matter is TAB LALB, this is for dimensions, and lo and behold, the heat density of geometry can be interpreted as RAB LALB with the correct sign. This has not been put in by hand, it comes out with a minus sign, plus there are further quantum gravitational correction. This is the lowest order relic which you get. Now, if you do that, you are going to extremize it. The equations of motion which you get will have this form. RAB LALB will be proportional to TAB LALB. This was first derived by in a paper which Asim and I wrote from a different perspective, and then it has been developed much further in the emergent gravity paradigm. So, you get an equation like this, and this equation depends on LA. What is being claimed is that this equation should be true for every null vector LA. Then one can immediately show that this is equivalent to this GAB being equal to TAB plus some constant times Kronecker delta AB. So, your equations of motion are invariant under TAB going to TAB plus a constant, but the solutions to the equations of motion has one undetermined constant. This is how cosmological constant comes in. What happens here is that this TAB LALB, if you look at it for simple gadgets like ideal fluid, etc., will have the form rho plus P. This is just to connect with something you know. In general, it is going to be the heat density. Even when TAB, for example, if you take the TAB contributed by the Coulomb field, it has no thermodynamics. But as far as the local Rindler observer is concerned, the TAB which is crossing the null surface, he will always attribute to it something like a heat density, and that heat density is going to be this P plus rho, and it is not the geometry is not reacting to the energy density, unlike in conventional general relativity, but it is reacting to the heat density. That is why it is immune to cosmological constant, because for cosmological constant P plus rho is 0, it does not come in at all, and it has to come in as an arbitrary integration constant, and you need some other physical principle to fix its value. So, this is the way it is going to be approached. So, just to summarize what I have said, you make the variational principle invariant under this L going to L plus constant, because I claim it is a symmetry in the matter sector, and it has to be preserved by everything in the world including gravity. So, I rise it to a status of a postulate. Once I have got that, rest of the way is fairly straightforward. So, if you want to have, the natural choice is to use TAB LALB suitably, which gives you temperature times the entropy density, which is the heat density. Then it cannot be done in any local generally covariant theory if you vary metric. So, metric is not going to be the dynamical variable. Metric is some long wavelength coarse grained variable like density or pressure in a fluid. All through today's talk, it would be good if you keep in the back of your mind the picture that space-time is like a fluid, like water. Okay. So, microscopically there are atoms or degrees of freedom, that is a better way, but atoms is more figurative and dramatic way of talking about it. But any atom you can actually think of as degrees of freedom which is capable of exchanging energy and momentum. That is all which we need from out of an atom. So, there are microscopic degrees of freedom in a fluid, and then you can describe fluid in different levels which I will describe to you in a minute. So, you have metric is not going to be a fundamental degree of freedom of the theory. The variational principle will involve TAB LA LB which is the heat density of matter, and there will be an RAB LA LB with some constant which is going to come from the geometry. We have to see where it comes from. And the LA is a null vector, and you claim that this has to be extremized with respect to every LA. Once you do that, you get an equation, and that equation is invariant under TAB going to TAB plus a constant. But the solution to the field equations will contain lambda as an integration constant. Ultimately, I should have some physical principle to fix its value, and when you fixes its value, it better come out tiny and is comparable to what we have been observing in the universe. So, you need a microscopic theory to give meaning as to why LAs are singled out, what is so special about null vectors. From top down we understand, because null vectors are normals to null surfaces, and null surfaces act as horizon to local Rindler observers. So, the thermodynamic connection connects these null vectors to what we are doing, but you should also have a meaning from the microscopic end, and we will see that it does get a nice meaning from the microscopic end. Fine. So, the big picture is that you can divide entire story into three levels. One is what I will call the macroscopic scale, the other is what we will call microscopic scale, and for want of a better word, in between I call it mesoscopic scales, which is borrowed from some condensed matter terminology. So, in the macroscopic scale, you are talking about a continuum limit of a thermodynamic system which is sitting in this microscopic level. There the metric is like a fluid variable. So, it is like density, velocity, etc. of a fluid, and in fluid you will write a Navier-Stokes equation and a continuity equation. Your field equations are like that. In this level, I will show you that you can actually count the microscopic degrees of freedom. This we could do even in chemistry. The Avogadro's number was known even much before we knew the atomistic nature of the matter, but we did not know what we were counting. It is actually we were counting the number of molecules in a gas or something like that. In the same sort of way, we do not know what atoms of space-time are today, but we can count how many atoms of space-time are there. Whenever I say atoms of space or atoms of space-time, think of it as intrinsic microscopic degrees of freedom, which does contribute at the macroscopic level as a relic. Not everything will contribute. Like if you are talking about kinetic theory for a fluid, then you write down a distribution function. You essentially attribute momentum and position to a molecule. But molecule has lots and lots of internal degrees of freedom, but they are not relevant. In that sense, here only a null vector is going to be relevant, everything else will be subsumed. This line is important because there are several such attempts. This has now become a fashionable area. So, there are several such attempts to link thermodynamics with gravity. But what is very important is that if you derive Einstein's field equation out of thermodynamic argument, that is not good enough. You have to give a completely thermodynamic meaning to the field equation, which we will see can be done. And as you can imagine, as you go from macro to micro, these are much more definitive in the sense that we know what is going on here. As we go down, things are going to become slightly more speculative. So, next you have a mesoscopic theory. The difference between a fluid variable like this and a mesoscopic theory is that here you are assuming it is a complete continuum. You are not talking about number of molecules. But the moment you come to kinetic theory, you are going to say that you are using some kind of a function to count the number of particles, and you are distinguishing different particles at the same point by an extra label P. Something similar is going to happen to space-time, and this extra label is going to be your null vector. And this discreteness comes in because you are going to say that there is a minimum length in the space-time. That brings in the second ingredient. The cosmological constant has come in here, The second ingredient, Planck length square, comes in here. It also will appear when you are counting this, but this definitely appears here. And this will allow you to determine the omega grav, and you can maximize this, and then you will get your correct result. At the third level, you need some microscopic theory of pre-geometry, and there the only place where I could sort of make some progress is in cosmology. This 0 point length also allows you to determine in a very natural way the information content of microphysics. The unit of information turns out to be a number like 4 pi. If you use this and you think of a picture where the universe evolved from pre-geometry to geometry, which is what you call cosmogenesis, this lambda comes out as a relic from pre-geometry and its value can be fixed. So, this is the overall picture which we are going to talk about. So, when you do this, the sort of take home point about this approach, especially if you go and read other approaches like based on entanglement, etc., I want to emphasize 3 aspects which singles out the program which we guys have been involved in compared to every other approach which other people have been doing. The first point is that the space-time dynamics should be described in thermodynamic language and not in geometrical language. This is extremely important. There are several papers available in the market which will somehow derive Einstein's equation from thermodynamics. So, if you finally write down capital GAB is equal to TAB, you have lost the battle, you might as well go home, because capital GAB is a geometric object. So, what we are talking about is that gravity is like the thermodynamic life of some system, and we know the kind of variables we use in thermodynamics like temperature or heat, things of that sort. So, you have to write you should be able to show that the standard Einstein's equations can be reinterpreted entirely in thermodynamics language. So, I am going to spend some time doing that. It is not deriving Einstein's equation, it is just re-expressing Einstein's equation in thermodynamic language. That is extremely important, because if you cannot do that, if you just derive a geometric thing out of it, it doesn't make sense. Yes. Yeah. That is. No, it is not. It is going to be the heat density of geometry. That is fine. RAB is what expresses it, but RAB equals TAB is a geometrical statement equated to a matter statement. But TAB, LAB, LB is the heat density of matter, and if the other quantity is a heat density of geometry, or rather actually it will come with a minus sign. So, essentially what you are saying is that there is no net dissipation in a null surface. So, it is completely a thermodynamic state. Okay. Okay. Second, this is slightly off the main course, but I think you should know this. This connection between gravity and thermodynamics is not restricted to general relativity. The point is that in general relativity, we have seen that the entropy comes out proportional to area. Area is such a nice quantity that once somebody tells you entropy is proportional to area, you can come up with some 4 or 5 ways of deriving it. Okay. But there are a whole class of theories. In particular, there is a class of theories called Lankos-Levelock models, which I am not going to go into, but for which the entropy density, entropy times an area, will come out to be the area upon 4 LP square. This is what you will normally have. It will get multiplied by a more complicated tensor. Almost everything which I am saying here extends to these theories. So, this is in some sense like saying that thermodynamics applies to all systems. The temperature is independent of the system. I can keep a metallic scale and a glass of water at the same temperature. But if I tell you the entropy as a function of other variables of the metal or entropy as a function of other variables of the glass, you know a lot more interpretation, a lot more information about the system, and you can interpret what is going on there. This is something very similar happens here. The entropy density's expression determines what is the theory you are talking about. You can reverse engineer that. Once I know the entropy density, from this approach, you can get back the field equation and you know which theory you are talking about. But the temperature is more a kinematic object that just says what local Rindler frame you are working with. The third ingredient is that we are not doing philosophy. So, if you are going to say something about quantum theory of gravity, you better come up with a number which you can check somewhere. Okay. At least you should have a way by which you can go forward and come up with a falsifiable number. And you will find that in this particular case, three things happen. First, it gives you tremendous insight about classical gravity itself. Several things which are like coincidences in classical gravity fall in correct place. Second, it tells you something about the microstructure of space-time, not a lot, but it tells you something like the correct variables to use. And finally, it gives you a numerical value for the cosmological constant, which seems to tally with what we have seen. So, there are obviously other postulates involved, but within this postulate, it gives you these three. So, which is a step forward. So, let me start with the macroscopic scale of gravity, which is the fluid mechanics of space-time and how you count the atoms of space. So, the main paradigm shift here is that the field equations of gravity, any theory including Einstein's theory, has the same conceptual status as those describing, let us say, elasticity or hydrodynamics, okay, any kind of fluid mechanics. Now, this is important because this tells you already why the conventional approaches to quantum gravity are doomed to failure. The point is that suppose you take a solid and you have the elastic vibrations of the solid, and that equations can be written down. It has a life of its own. Given a few constants like Young's modulus, etc., you can write down how a cantilever will vibrate. No sensible engineer will ask you what are the Schrodinger equations of the atoms before constructing a bridge. So, it is completely self-contained description, like Einstein's field theory. Einstein's gravitational field equation is a self-consistent description. It is just like elasticity. It is the elasticity of the space-time solid. Now, what happens is that suppose you are vibrating and you have vibrations and you write down those equations and you quantize them. You will get beautiful physics. You will get the physics of phonons. The phonons are the quantized lattice vibrations. You can study phonon scattering and how phonons interact with others. You will probably be able to explain phenomena in the solid. You are not going to get the atomic theory of solid. You are not going to understand the structure of the solid. So, all these approaches where you take G mu nu and you quantize it will get you gravitons, so to speak, or some superficial level of quantum properties of the underlying space-time, but it is not going to tell you what is the structure of the space-time. So, the main ingredient where you talk about the thermodynamic approach is a famous line from Anderson that more is different, okay, and that is exactly what thermodynamics tells you. You start with microscopic atoms or molecules, it has things like energy. But the moment you go to thermodynamics, there is something else called free energy. This is unique to thermodynamics. And the E minus that free energy, this difference gives you the Ts, which is the heat density. And the heat density is a new concept which comes up in thermodynamics. You cannot talk about heat density in microscopic physics. This is a thermodynamic concept. And that Ts, this heat density which I have written down, because of the Gibbs-Duhem relation, is equal to P plus rho, and that can be written as this TAB LALB. And normal matter we know has heat density. What we have discovered in all these, and the moment you have heat density, you can think of it as entropy density except for a scaling. You can think of it as information density because of the connection between information and entropy, and the information density will tell you what is the microscopic density of states. So, I will do the jumping between these concepts depending on what is most convenient at every appropriate stage, but you should think of these as a continuum in the sense that these things are interlinked concepts when you do your maths properly. The point which we have understood in the last several lectures is that space-time also has a heat density. Take any event, you can associate a temperature and entropy density just like you can do it with a glass of water. So, for the moment let us stick with Einstein's theory, then the entropy densities are proportional to area, and the temperature is something which is given by the local Rindler observer. Of course, this fact transcends black hole physics, because in black hole physics everybody understands that there is temperature, entropy, etc. But as I said, black hole horizon and its temperature itself is only a special case of any null horizon exhibiting a temperature and entropy to a particular class of observers. Black hole entropy and temperature are heavily observer dependent. There is nothing absolute about it. If a guy who is falling into the black hole, he will not see the temperature, he will not attribute an entropy. Just like if you have a Rindler observer and an inertial observer, one guy will attribute a temperature and the other guy not. So this brings us back to something which was raised very early on by somebody in the audience, that will I finally end up getting a field equation which depends on the observer? No, they are going to be generally covariant. So I want to talk a little bit about general covariance. The point is that suppose I write down an equation, let us say some tensor 0, 0 component equal to some other tensor 0, 0 component. And I ask you whether it is generally covariant. You will say, of course not. I mean, after all, you are using 0, 0 component, so you have to tell me which frame you are working in. If you go to another frame, it will mix up with A11s, let us say. And until you tell me how A11 is related to anything else, this equation will not maintain its form. True. Now let me write it in a different way. I am going to write it as AJK UJ UK is equal to BJK UJ UK, and I say that in a given frame UI has the components 1, 0. Okay. So this equation is same as this equation in that frame, but these are generally covariant scalars on both sides. So this equation I can transform to any other frame. Of course, in a special frame like the rest frame of this, think of it as a 4 velocity of an observer. So you have an observer, and in the rest frame of the observer, this is going to give exactly this. So if I say that in the rest frame of a particular observer this equation holds, you will say, okay, I don't know what is going to happen to another observer. But if I say that given a 4 velocity of an observer this equation holds, then again for that observer you know how to transform. Now I tell you something else. I say that this holds for all observers. Then the only way it can hold is that you can cut these two things out and say this is equal to this. So this is how general covariance is going to come in all our discussion. We will have an observer, a local Rindler observer, he is going to see a temperature, he is going to have all kinds of thermodynamic phenomena around him. Then you get a result out of him. Then you say that for all local Rindler observers at all events in space-time this should hold true. And that will give you a purely tensorial observer independent expression. This is how you end up getting that. And for every observer you will have a physical interpretation in terms of thermodynamics, which you won't have if I just write down Aij equals Bij. AJK UJ UK might have a nice interpretation. For example, if this is like energy momentum tensor, this is like energy density. So, it is saying that energy density is equal to some other energy density. Okay. So, you can give physical meanings to these equations much better than physical meaning to this component form, and that is what will happen. Okay. Now, I have already told you this, T is independent of theory of gravity and S depends the theory of gravity, but we are not going to discuss other theories of gravity. The entropy density arises because you can have regions of space-time which is inaccessible to a class of observer, and this inaccessibility is what gives you the entropy. You are again saying that information is going to play a lot more role in today's talk than in all the previous lectures, and we will keep seeing this. It also tells you that you have to take non-inertial frames very, very seriously, because the non-inertial frames is introducing new phenomena. It is going to make your thermodynamics completely observer dependent. Suppose you are sticking with one very specific Lorentz frame, then you wouldn't discover Lorentz invariance, because Lorentz invariant comes up because when you compare two frames, and if you generalize it to general covariance, you discover new physics and new ways of thinking about it, and that is important. So this is just to remind you again that at any local region you have vacuum fluctuations which are going to appear as thermal fluctuation, and this is the guy we are going to concentrate on, and it will be as close, we will take a limiting case of as close to this null horizon as possible. This is for reasons I explained to you yesterday, that in the Euclidean plane we do not want any curvature corrections to come in, so I want to be as close to the origin as possible. That circle has to be very close to the origin, which is like saying that this has to be as close to the horizon as possible. So if you do that, then you can prove, this is important contribution by Ted Jacobson, that the heat transferred due to matter crossing the null surface has this form. This I already mentioned to you. Now, those of you who know a little bit of general relativity, I can orient you towards that. Essentially, if you have TAB times velocity, then that is going to give you the momentum, right? And then if you have a normal, it tells you the amount of momentum flux through that region, and that will be like the heat as far as this guy is concerned, because he will attribute a temperature to that. Except that normally these vectors are not going to be null, but what happens is when you go close to the horizon, and if it is a null surface, then the normal is going to be the null, and you will find that both of them turn out to be LAL. Okay? This is derivable, but I am not deriving it for you. And remember that this null horizon also has an important role to play in the Euclidean origin. I told you there is this normal, and when this sphere is going to go to this point is your null horizon. You do not know which way to draw the normal. So, there is a fluctuating normal there, or rather a normal whose direction is unspecified, and you may have to take all possible normals in order to construct a case. This will come up later on. Fine. Now, you come back to this question of counting the microscopic degrees of freedom, and this is not as difficult or as esoteric as you might imagine. The point is that is exactly what has been said this. Suppose you take a glass of water, you have molecules and they are angstrom size object, and if you have a microscope which can probe those scales, you can actually see the molecules. But you can guess that the water is made of atoms or molecules without probing it at angstrom scale. And this is precisely what Boltzmann did. He said that if you can heat something, it must have microstructure. Now, those of you who are interested in history of physics, I keep emphasizing you should go and read this part of the history of physics. It is very fascinating. It tells you how enormously smart people who have made brilliant contribution to physics can go completely wrong and get stuck in a local minimum of idea and lose their lifetime. There were two times which happened in physics history so far. One is when people were attacking the problem of heat. Many people believe that heat is like a fluid, like a calorific fluid, which has strange properties, and you have to transfer from one place to another, and it should have various behavior. A completely different place where this happened was when people got very enamored with the ether theory. And ether was a very strong temptation for many people. People like Lorentz, who came up with the Lorentz transformation, extend electron theory, the other Lorentz, etc. Many of them spent their time trying to figure out, for example, electrons as vortices in the moving ether. So, you think of vortices in the ether, because elementary particles were being discovered around the same time, and we did not know what they are. And it took genius of Boltzmann to throw away calorific theory. It took the genius of Einstein to throw away the ether. Okay? So, it can very well happen that very smart physicists get stuck in a completely wrong idea and waste their lifetime. And what Boltzmann did was to correct this notion, and he said that you do not need any of this nonsense. Material bodies has microscopic degrees of freedom. He did not know what they are. Atoms and molecules were known at that time, but he could conjecture and show that in order to store an energy delta E at a temperature T, you need this many degrees of freedom. This I had already told you earlier on. This is thermodynamic, this is thermodynamic, this is statistical mechanics. So, the microphysics statistical mechanics leaves its signature on the macrophysics. If I can measure this and measure this, I can measure this. That is what we will do with gravity. We know that you can heat up space-time, space-times have temperature. So, you want to have some kind of a microstructure. We do not know what it is. Boltzmann did not know what atoms and molecules were. But can we count them? Can we count how many microscopic degrees of freedom are there as, let us say, the atoms of space or space-time? What happens is the following. You can actually do that. When you do that, you get a very nice result. We saw this result in the case of black hole space-time, but it is a very general result. If you take any static space-time and you take a volume and you take the bulk energy contained inside the volume. So, this is normal three-dimensional surface which I am talking about. There are some special special kind of surfaces for which this equation simplifies to this form. We will come to that. But you take a bounded surface and it has a surface area and surface property. So, this is normal three-dimensional space in curved space-time. There is a total energy E bulk which is contributing to gravity. It is called the Komar energy inside. Then on the surface you attribute dA by LP square, degrees of freedom for a small element dA, and then you add half kB times the local under root temperature at that point. Then you will find that this integral on the surface, which I can think of as dN times P local, is actually equal to this E bulk. Black hole spacetime is just a special case of it. Now, this tells you that you are associating with dA this many degrees of freedom. It is just like saying that in some volume dV, if you have a distribution function f into d3x d3p is the number of particles in that volume. Of course, d3x and d3p, if it is mathematical infinitesimal, then you can't do that. But you assume that there is a intermediate scale at which this can be defined meaningfully, and that is exactly what is happening here. What is more, this relation I have written down extends to all Lankos-Lovelock models, and the density can be written down for that. Okay, but we won't go into that. Fine. So I want to give you, since I didn't derive it for you, I wanted to show you something curious, that this comes just from Gauss theorem in Newtonian limit. Okay. So we are going to do a little bit of mixing of scales to prove this for you. So suppose you take area divided by LP square and you want that to be equal to the bulk. The number of degrees of freedom in the bulk you define as the gravitating energy divided by the average Andrew Davis temperature on the surface. So if you take a bounded surface, imagine that to be the surface of a microwave oven. Its temperature is not a good microwave oven, so its temperature is not strictly constant, but it is varying. But I can define an average temperature. Now if I put something inside it, if it reaches equipartition, I am not saying it will reach equipartition. If it reaches equipartition, then the number of degrees of freedom inside will be the energy divided by half k. Now what this equality tells you is that in all static spacetime you have reached the equipartition. In any static spacetime, the surface degrees of freedom is equal to the bulk degrees of freedom. So let me show you how this comes about when you are doing Newtonian example. So what I have got is half dA upon LP square kB Tc. This half kT is coming in here, and there is a dA upon LP square. So write this E as energy density times dV. On the right hand side, this is 1 over 2 LP square dA. Temperature ka expression is h cross upon C into G over 2 pi. Now I am going to choose now the surfaces which are equipotential surfaces in Newtonian theory. So if I take equipotential surfaces, they have a normal and the acceleration due to gravity is minus g. So g dot n integrated over an area, you use Gauss theorem. So that is going to be divergence of g, and you have a h cross C and this 2 pi, that is going to give you this constant. So I got a volume integral here and a volume integral here. So I get divergence of g to be 4 pi C LP square upon h cross times rho. Rho is the energy density. So you can divide by an energy density square and put a C cube here. So you get the, then you translate this LP square to the convention. I am not happy with this last step, but that is how one would have gone about conventionally. You would define LP square as g h cross upon C cube. So then when you put this, you get this equation. This is just your standard Poisson equation. So the Poisson equation you could have reverse engineered and got this. Of course, you need this crucial ingredient that there is a temperature associated with the acceleration, that we know only from quantum field theory in curved spacetime. Okay, that is just an example. The way it happens in general relativity is the following. This is normal 3-dimensional space at a given time, and you take a equipotential surface. There is a natural way of defining equipotential surfaces in static geometries. It has a area and there is n surface, which is area upon LP square. There is a normal here, and that normal gives you an acceleration due to gravity in the other direction, and you have observers who are sitting there. And there are also freely falling observers, and I have told you that relativists think freely falling observers are not accelerating, while the people who are sitting there are accelerating. So they will have a local G local upon 2 pi temperature at every point, and that will vary across this. So you can define an average temperature, which is the integral of this divided by area. Then you take the total energy inside, and you divide by this average temperature to define an n bulk. So the n bulk is just a definition here. This n surface is something which you can count. Then what happens is that if you assume space-time is static, the Einstein's equations imply and is implied by this simple statement that this n surface is equal to n bulk. That Einstein's equations implies this is straightforward to derive. In order to show that Einstein's equations come out of this, you have to assume that this holds for all equipotential surface and all observers. This is exactly what I mentioned here. This is just a scalar equation, but the scalar equation depends on what equipotential surface you are drawing, what observer is measuring this temperature. The moment you say that it should hold for everybody, it has no go except for Einstein's equation to follow that. The condition we have used here is that the space-time is static. Okay? There is no dynamics in this space-time. So, it has reached equipotation. In rough sense, you think of it like a thermodynamic equilibrium at very large scales. Okay. What happens if it is not in static case? So, in static geometry you get this, but if it is not in static space, then there is going to be some heating and cooling going on. So, the time evolution of geometry, what you thought Einstein's equations were giving, is actually going to describe the heating or cooling of the geometry, underlying degrees of freedom, and that will turn out to be proportional to n surface minus n bulk. So, the time evolution will stop when n surface reaches n bulk. The deviation between these two is what is driving it to this equipotation. The precise equation, in order to derive that, I have to introduce some variables. Almost all of you will be familiar with the metric tensor, but it turns out that there is a more natural set of variables when you are studying thermodynamics, which is square root of minus g times this GAV. This was originally used by Einstein himself, but then it was sort of fallen on the wayside, but we sort of resurrected it. And instead of standard Christoffel symbols, you use this linear combination of Christoffel symbols, which I call P. There is a reason why I call it P, because if you think of this as Q and you take the Lagrangian R root minus G and you calculate the canonical momentum attributed to this, normally you would have taken Q dot, now you have to take all the derivatives, so one more index will come. This is actually the canonically conjugate momentum corresponding to this in standard Einstein state. So, this QP are very well defined canonically conjugate variables. Then what you will find is that the P delta Q and Q delta P with indices contracted suitably, one can show on any null surface corresponds to S delta T and T delta S. So, the thermodynamic variations on a null surface corresponds to dynamical variable. So, the first thing which we have done is that what you thought was geometrical variables have been given a completely thermodynamic interpretation. Now, it is just one step to actually write down the Einstein's equation or the evolution equation. What happens there is the rate of change of this P. Now, this needs a little bit of technology. This is what is known as a Lie derivative with respect to your time vector in the space time. If you do not know what is a Lie derivative, just think of it as like time derivative. It's a time derivative with a graduate degree. Yeah. Yeah, P is a well defined tensorial orbit. In the sense that tensorial in what sense? You are saying it is built out of Christoffel symbol? Yeah, in that sense it is not. So what is the? No. The Lie derivative of P is a purely invariant probability. It is a tensorial object. P by itself is not. The Lie derivative of the Christoffel ordinary Christoffel symbol gamma AB. If you take the Lie derivative with respect to any vector field, you get things which can be expressed in terms of curvature. So, that is a tensorial object. So, this object is a purely tensorial object. This is a purely tensorial object. There is a root minus G that will be taken care of. But P itself is not a tensorial object, but I am not bothered by that. And in fact, that is the philosophy which I am trying to get you out of. If it works in a particular frame and then I say that it works for all frames, it is as good as working with a tensorial object. Okay? So, I am not too bothered about a tensorial object, but in this particular case it turns out that this full thing is tensorial, this is tensorial, everything is generally covariant. This equation remains form invariant. Okay? But I would not make too much out of it, because in order to define this I have to define a T average. T average is going to require my Davis unroot temperature, that is going to introduce some foliation and some observers, right. So, I am not bothered by the fact that I have a foliation and observers in this space time. What this equation tells you is that the so called time evolution of the space time. Remember, this Q and P are like S and T. So, this is like a T delta S. It is the heating of the space time which we are talking about. The heating or cooling of the space time is driven by the deviation from holographic equipartition. Again, this is a single equation. It is implied by Einstein's equation, that is easy to derive, and it also implies Einstein's equation the moment you assume that this holds for all observers, all local frames and all Rindler observers. So, that is why I said that I do not want to think of it as a major victory that this is a tensorial object, because I have other creatures which depends on the observer. So, the correct way to think about this is that something has to hold true for all observers, then that tensorial quantity comes out of. But now we have succeeded in the first task I mentioned. I no longer write GAB equal to TAB. I tell you that there is a surface degrees of freedom and bulk degrees of freedom, and the deviation between them drives the evolution of the space time, interpreted as heating and cooling. So, it is Einstein's equations are completely described in thermodynamic language and not in geometric language. Okay. It also, I told you that it, yeah. Q is a tensor. It is a tensor density. It is root minus G times GAB. Let me give you the definition once again. This is Q. It is a tensor density, and this is not covariant at all. But as I said, get out of this trap of thinking covariantly. Think in terms of observers and say that it should hold true for all observers. Okay? Yeah. Right. Any other? No, the point is that this is what comes out. This comes out of the emergent gravity paradigm, and it turns out this implies Einstein's equation. So, there is nothing which I can do about it. Okay? If you have to get Einstein's equation and that has to imply, I know exactly what it implies and is implied by. There is no choice here. Nothing has been assumed, nothing has been postulated. It is just re-expressing standard Einstein's equations. Yeah. Right. The way one is deriving any of these equations in this thermodynamic paradigm is thermodynamics is observer dependent. If I write down an equation TdS equal dE plus PdV, it is meaningless unless I tell you which observer it is. Then how can I say TdS equal dE plus PdV is valid? It is valid because it holds true for all observers. That is how you built in the covariance, even though the terms you use to interpret this is observer dependent. This is exactly this. I take an observer with a 4 velocity uj. Then if I say that this holds for a particular uj, I do not go any further. But the moment I say it goes for all uj, it is going to give you this relation. Something like that. I mean, one of them is, I do not quite remember which one is which, but I think Q is like entropy and P is like temperature. It is S dt which you get. Yeah, right. It is interchangeable because you will pick up a total derivative, and in this game you have to be careful with total derivatives. You have to take into account the heat density transferring through the other one, then you can interchange it. It's just like thermodynamics. If you have an equation with TdS, you can write it in terms of S dt. You can do that. Okay? Then there is a d of Ts, right? That d of Ts you have to be careful about. Yeah, right? Right. That is correct. That I showed you the other day. Yeah. Correct. Absolutely. Absolutely. And that will tell you exactly what this is. Okay. Exactly. So, there is a, I mean, this is again technical thing. There is a lot of difference between some equation not being generally covariant and some equation depending on the foliation. These equations are foliation dependent, but it is actually genuinely covariant when you say it holds for all foliations. Yeah. Okay. Now, let us proceed a bit further. I told you that it gives you insights about general relativity itself, and I wanted to talk about one result which is just remarkable, okay, and it is not completely explored, so there is some scope for that. If you take matter, we all say that there is an equation like this, which is almost like a conservation law. It is not quite a conservation law, but it comes from a local conservation law in special relativistic ends and written in a generally covariant way. But what is the momentum associated with TAB? There is no way you can write down the momentum associated with a particular TAB without telling me which observer you are talking about. So, if the observer has a velocity Vb, then this is the momentum associated with it, and you take the divergence of that, that will not be 0. So, the momentum of matter is not covariantly conserved. I mean, this is a nice vector field. So, if it has been 0, then I could have integrated and got a conserved quantity, unlike this equation. But it is not conserved. Momentum of matter is not conserved. Why is that? Because you did not add the momentum of gravity. So, if you take the momentum of matter and you add momentum of gravity and you take a divergence equal to 0, that should give you Einstein's equation. Just as this gives you the matter field equations, any matter equation can come out of this conservation, so quote unquote conservation law. The gravitational field equations will come out of momentum conservation. Yeah. Absolutely. There are very special cases where it will hold, but I am talking in general. If you take a given observer, it will not hold. There are no killing vectors in an arbitrary space time. Right? So, anything which works only for killing vectors is useless for me. I am trying to formulate the theory in the most general sense. So, the reason, and also you will kill yourself on the wrong track because of that, because it is telling you that this momentum is missing some momentum, and what it is missing is the momentum of the geometry. So, there is people who spend lifetime trying to find a TAB for gravity. What is the stress tensor of gravitational energy, stress tensor of the gravitational field, so that the total conservation will give you Einstein's equation. And there is a theorem which says you cannot write down a local conserved along with the TAB, which is generally covariant. But momentum is a very different creature, and somehow people did not look at the momentum. The reason people did not look at the momentum is that trap which I am trying to get you out of, that it is observer dependent. You need an extra velocity field to define the momentum. So, the momentum of the geometry or the space time depends on which observer you are talking to, and that same observer will attribute a momentum to matter, and if this equation holds for all observers, this is a scalar equation, it is a single equation. If this equation holds for all observers, it is equivalent to Einstein's theory. Now, this momentum comes out of this emergent gravity paradigm, is given by this expression. It might look a bit strange, but it shouldn't. It is just, this is like the Hamiltonian from a Lagrangian. So, let me just orient you on that. So, Hamiltonian is PQ dot minus L, right. What I have got here is R is like L, so think of it as L. Then I have put minus, there is a Q and a P, so QP dot. This is what I am looking at. But this L is actually LP. Remember, I told you long back that there are two kinds of Lagrangians, and in gravity what you have to fix in the boundary is like the momentum. So, this LP happens to be LQ, the standard Lagrangian you are familiar with, minus d by dt of PQ. So, that is minus Q dot P minus P dot Q. So, you plug this in, then this Q P dot is going to cancel out with this, and you end up getting here minus LQ. Inside this I have this is plugged in here, minus Q dot P. So, this is PQ dot minus LQ plus QP dot. Okay. So, I am missing a sign somewhere, let me just get this right. Yeah, that is right. Okay. So, once you do that, you are going to end up getting exactly this object, minus L minus this is minus. Yeah. So, it is minus L plus PQ dot, which is H. So, that is exactly what you have here. This is Lagrangian and this is QP dot. Now, everything comes with sophistication. You do not take a dot of this, so you take a Lie derivative with respect to a vector field, and you want an extra index here, so you throw in this VA. So, if you take VA equal to 0, 0, 1, 0, 0, 0, it is going to correspond to Hamiltonian. Yes. Q what? Yes. Oh. Yeah. Right. Something like that. That is correct. That is exactly how the LQ quadratic and the R root minus G play out. Yeah, that is right. But this is what is the most natural momentum definition. You would have written down, if you start with the LP, which is what everybody starts with, R root minus G, but understand that it is an LP Lagrangian, then this is the combination you will look at. Then it turns out that if you take this and add to it, this depends on vector V, which is the velocity vector of the observer. So, different observers are going to attribute different momenta to the same geometry, and then if you write down this for all observers, it implies field equation. So, it tells you something further. I said it comes from the thermodynamic paradigm. What it tells you is that when equations hold, if you again calculate the energy, total energy of matter plus gravity in some bulk region, it will turn out to be exactly equal to the heat flux, or rather the heat density Ts integrated over the surface. So, you will again and again come across this idea that there is a heat density on a surface, the total of that is equal to the total bulk energy inside. And this is a restatement of equipartition, n surface equals n bulk, etc., etc. All these are connected. You can derive each one from the other. Yeah. Script P is the total momentum. It is the sum of the momentum of the matter plus matter plus gravity. And this equation is on shell. Okay, there is an off shell version, but the on shell is fine. And again, I have said this is generally covariant, but foliation dependent. I will never work with killing vectors when I am doing this sort of thing. Okay, because that will give you very misleading ideas and it will not give you the general evolution. Remember that general spacetimes do not have killing vectors. Killing vectors is a construction of lecturers in general relativity because they want to solve things. Okay. So, now let us go to the next stage. This is also another place where the momentum plays an important role. Take a null surface. Yeah. Take a null surface and you dot it with 3 of these objects. LA is the normal to the null surface, and normally null surfaces come with another what is called an adjoint null vector. Roughly speaking, if I have a null surface like this, there is a null vector in this direction and a null vector which is lying on this, and these are L and K. And then once you have taken the L and K out of the metric, there is a 2-dimensional creature which is the 2-dimensional metric on the null surface. So, given this momentum, you can take these projections. You take Einstein's equations, or rather you do not have to even take the Einstein's equation, you take these projections and compare it with Einstein's equation, and you will find that Einstein's equation itself can be rewritten as one equation which is a Navier-Stokes equation which will come from this, another equation which will actually translate into TdS equal dE plus PdV, and yet another equation which will tell you the evolution equation for the null surface. Yes? Yeah, right. Right. You have to take the energy density of the external force field and put it into it, and everything will be fine. This is why you do not have Lana-Weichart potentials in general relativity. There is no such thing as the field of an arbitrarily, gravitational field of an arbitrarily moving particle. Particles do not move arbitrarily. You push, and once you push, that object contributes to gravity. Okay. So, I again want to give you a simple illustration because I am not giving you derivations. So, imagine you have a gas of molecules and a piston, and you think of 2 equivalent equilibrium configurations mentally, one where the piston is here, other the piston is here. Do not think of it actively like moving things up and down. You are just think of 2 equilibrium configuration. Piston could have been here, tomorrow I come and draw the piston here. Similarly, you think of a black hole which had a horizon here, and tomorrow I consider a black hole whose horizon is here. Now, it turns out that Einstein's equation, this textbook, you just look up a textbook, you can write down the Einstein's equation, which will turn out to be equal to this, where P is the pressure due to this medium around. I am not even assuming the horizon exists in a vacuum. There could be a pressure there. For example, if it is a Resner nostrum, there will be a pressure due to the electromagnetic energy density. Look at this equation. You can immediately, well, not immediately, if you think a little bit about it, if you multiply it by suitable factors, suppose you multiply it by a dA, then you can write this particular quantity as d of 4 pi by 3 a cubed. So, similarly, you put a dA here and then you can combine this and you can get this c to the power 4 upon g dA. Then you put a dA here and then something very interesting happens. You have to throw in a h cross here and you have to throw in a h cross. Then you will get T ds equal dE by plus P dV. Okay. This is dE because it is when you are talking about the it is gm by c square inverted, and this is going to be P dV. I have written down P and dV, and this is going to be 1/4 of the surface area, which is ds, and then I have to bring in the temperature by putting this h cross. This is exactly what happens in thermodynamics. Thermodynamics knows nothing about Boltzmann's constant. You throw in a Boltzmann constant here to convert it into energy, you throw in an 1 by Boltzmann's constant to get into this, and then these two things cancel away. The TdS level, this equation knows nothing about h cross. This is classical Einstein's equation. That comes because you had a h cross and a h cross cancelling. Just like in this statistical mechanics, it cancels. So, this can be extended to several cases. This is the way we started this entire program, so people looked at this in different cases, but we know where it comes from. And the same thing happened for Newton's law. If you use this approach, then what is fundamental is h cross c and LP square. I am actually running a bit out of time, but let us see. So, if you write down the Newton's law, you do not write G here, you write it like this. And if you think of LP square C and h cross as fundamental, which is what this approach teaches you, then when h cross goes to 0, the gravitational force blows up. So, gravity is fully quantum mechanical at every scale, just like matter is fully quantum mechanical at every scale. Of course, we talk about classical limit of matter. So, if you take a lattice and there is some sense in which you can get elastic equation from lattice dynamics, but you have to be very careful. There is a h cross inside the atom which you should retain to a finite value. You put h cross equal to 0 in an atom, it will collapse on you. And every other h cross which comes up in interactions, you set to 0. And there is a consistent way of doing it. But essentially, matter is fully quantum mechanical, and this tells you geometry is also fully quantum mechanical. There is an inherent structure which does not exist when h cross goes to 0. Now, let me go to the next level. All this is at the thermodynamic limit, rewriting Einstein's equation. Now, I want to ask whether there are statistical mechanics of the microscopic degrees of freedom can be guessed from this, can we relate to this, and you want to maximize the density of state for gravity and matter to obtain this result. So, the point of course is that you want to find what is the omega of matter we know, that is TAB, LAB, and from that you can obtain that. The omega of space time I have to figure out without actually knowing the full quantum theory of gravity. So, if you want to do that, you have to somehow recognize discreteness, but we should also be able to use continuum mathematics, because we are finally going to talk in terms of metric and all that. Now, it just so happens that we had already done it. We have never been taught like that, but we have already done it when we do kinetic theory. So, if you think of a fluid, the continuum limit has only one velocity field at a given point and one density field at that point, and it ignores completely the velocity dispersion, that at a given point particles with different momenta can exist, and it ignores discreteness. Now, the mathematical statement is that there exists a volume element in which there is sufficient number of molecules to do some kind of a physics, and this F counts how many of them are there. So, when you go from continuum to here, suppose you have been doing that, this is what Boltzmann essentially did, you have to discover this object. Just think about it, we are coming from top down. In thermodynamic description of a fluid, Navier-Stokes equation, continuity equation, various constant, there is no Pi. Pi is the momentum of the particles at a point. There are no particles. If different Pi's can exist at some point, that is what you call velocity dispersion, and you ignore that when you are doing continuum physics. So, you have to be clever enough to discover this object. In kinetic theory, we know there are atoms and atoms move, because they move, there is a momentum. In the atoms of space-time, we do not know what it is, and that is what we are trying to discover. So, this recognizes discreteness, but yet uses continuum mathematics, and at every xi it has an extra Pi, and many atoms with different Pi can exist at the same xi. So, you can think of Pi as a stochastic variable. At a given point, Pi can take all possible values, and if you only want properties related to xi, you average over it. But there can be an average momentum which gives you a flow that will give you this u, but there will be dispersion around it. Keep this picture in mind. So, what is happening here? I have just drawn the picture, and there is a fluid lines, and you have u and this. So, the moment you go to this level, you have this distribution function with different momenta can exist at this point. Suppose I want to count how many are there. What do? You take surfaces and you count how many are here, how many are here, how many are here, and you take a limit n by v, and that will give you the density. So, what do we do in the atoms of space? In the atoms of space, our motivation is that to this I have to add a hg, and we want to come up with a microscopic origin for this. The way we do that is the following. In order to count this, you need some way of introducing discreteness. This is postulational. This is the second postulate I am going to make, because somehow you have to introduce a 0 point length into it. So, we have talked about temperature, H cross relation. We have talked about lambda LP square cosmological constant to some extent, we will come back to that, and the third point is the LP square. So, the way you do this is the following. When you complete the computation by adding the LP square, you find that the points in a renormalized space-time, that is which is described by some kind of an effective metric, has 0 volume, but finite area. And that area allows you, that is this hg contributed by atoms of space, the number of degrees of freedom, so to speak, is proportional to an area associated with the event xi. Now, I have to give meaning to what you mean by area associated with a point or an event. Okay, that does not make any sense, and we have to make sense to that. So, in order to do that, I have to reformulate entire classical general relativity in a different language. This is just classical general relativity at this stage. What you can do with a metric, you can also do with a quantity called geodesic distance, which is sigma square of x prime, which tells you what is the distance between 2 points in a local neighborhood connected by a geodesic, and it is given by this expression. If I give you GAB, I can of course compute this. You can also show that the double derivative of this with a limit x going to x prime gives you this. So, if you give me sigma square, you are given me GAB. In principle, somebody gives you sigma square, I can get GAB, I can take the curvature tensor, I can write down r root minus g, I can vary it. Whatever you can do with this, I can do with this. And it has a great advantage that it is a biscalar, while these are 10 components. And because it is biscalar, it has greater level of coordinate invariance. Scalars just do not change, its numerical value does not change, but here it will pick up a matrix. For our purpose, what is interesting is that the discreteness which comes from this minimum can be understood as a modification of sigma square. So, the argument is that the minimal modification you need to take into account to connect to thermodynamics is that the distance interval in any space time acquires a 0 point length. It goes into some other function of S of sigma square. Now, what we showed in this paper is that this works for almost all S of sigma square as long as S at 0 is finite. But for illustrative purposes, I will take this. This is some L0 square whose value finally you have to compare with Newtonian limit of the theory, and it will turn out to be some 3 pi times LP square. So, but there is a 0 point. Now, you can ask the following question. This sigma square came from some metric. Suppose this sigma square has changed to this. Can I write down a metric? First of all, it is not going to be a local metric because this depends on 2 events, so it will also depend on 2 events. And in fact, it has to blow up when x goes to x prime, because when you are taking a coincidence limit, sigma square will vanish because it is an integral from x to x prime. So, if you want to get something finite, this has to blow up. So, you do not talk about at an event, you think of it as a biscalar. You think of it as a smeared distribution in the mathematical sense. But what you can do is that once you have this QAB, you can do geometry with it. And just as we did in this particular case, you took surfaces and took the limit. What you do is you take a point, you send out geodesics of some distance sigma. This is in flat space time, I am just taking this, and this is a sphere. So, you have the line element which you can write down, and you can write down what is root minus g, that will go as sigma square, and the root h, the area of this will go as also some product of this quantity. Now, you take, instead of this flat space time, a curved space time. So, you take a point and you send a geodesic like this, send a geodesic like this, are all length sigma, but they are no longer straight lines. And the geodesics has a tangent, each one of them has a tangent here, remember that tangent vector is going to play a crucial role. So, this is a equigeodesic surface, and you ask what is this root minus g, and here root minus g is equal to root minus h, and what this is going to be explicitly as a function of, it will pick up corrections due to curvature. And one can actually show that in the limit of sigma being small, root minus g and root minus h is the sigma square times whatever you would have got in flat space time. It picks up a correction where this epsilon is RAB NA. This is Gauss. This is how Gauss started thinking about curvature. That is, you sit in the North Pole, draw equigeodesic surfaces, you will get a latitude circle, get its area, take the limit, you will find out what is the curvature at the North Pole. So, this is classical differential geometry, you get an expression like this. Now, you take the next step. What you do is you repeat this calculation after adding L0 square. Now, you find something remarkable and surprising. The root q, which is like root g with an effective metric, it picks up an expression like this. I mean, at first you will think that you only added sigma square to this. I mean, there is the sigma square, you add to it an LP square. So, you get this. Okay. It looks like that, except that the prefactor, there is a sigma and a sigma square in the volume element. There is no sigma in here in the area element. Therefore, when I shrink this entire thing to a point, 2 dimensions win, and the points acquire a measure which is essentially this L0 cubed into L0 square times this RAB NA. What is NA now? NA is the normal to a geodesic which started out from the origin and went to some point, but it is not going anywhere anymore. So, it is all NAs which are fluctuating around, because you can throw geodesics at any point. This is that extra degree of freedom which we were looking for. When we went from fluid mechanics to kinetic theory, you got a PI, and when you do it here, it is this Ni which is going to come through. Now, what you do is that the log of density of states of quantum geometry at point P is going to be the area associated with the event P. I know what is the area associated with it. So, the log of the omega of space time turns out to be this limit, and it has this expression. Essentially, you pick up RAB, LALB, and this is like the momentum of the atoms of space time, if you want to be very dramatic. Okay? But this is the extra degree of freedom which comes in. This sign, this sign could not have been guessed. Of course, you can guess if you know what Gauss wrote or something like that, and this sign is crucial, because TAB LALB sign is already fixed for you, and unless it comes with a minus sign, the entire program fails. You won't get Einstein's theory. And so, at every stage in this program, we have been cross-checking it against whether it is giving us something more than we have put in. It does, and this sign is important. Yes. LA is not. That I will tell you in a minute, because you do it in the Euclidean and take the origin, and that is that picture. Okay. This is the relic from quantum gravity. So, here is your answer. The Euclidean origin maps to the local Rindler horizon, and the sigma square going to 0 limit picks the null vectors. This is the point. These are the vectors on these surfaces, and when you are going to the origin to this point, which is your surface, and this is your NA which you are talking about. That is, you draw your equigeodesic surfaces in the Euclidean plane, and you are going to go to the origin. The origin of the Euclidean plane maps to the null surface here. That is how I end up getting the point. Yes, it is not that the geodesic tangent is null. What I am saying is that, right, yeah, fine, yeah. Okay, fine. So then rest is obvious, because I told you that if you have RAB LALB plus TAB LALB, it is just 2 lines. I mean, this is what I told you long back. Me and Asim wrote the paper doing this, that if you vary this, it will give you this equation with an unknown constant lambda. So the next part is the most speculative part, and let me try to finish it in 15 minutes. So the question is, can we get something more out of this, whatever we have done? It turns out that this particular geometry described by QAB, if you have a geometry which has 0 volume but finite area, obviously something weird must be happening, right? What is weird happening is that the effective space-time dimension becomes 2 close to the Planck scales. Now, this has been conjectured by a huge number of people before us. This is earlier work. And there has been lots and lots of discussion that maybe space-time has to be 2-dimensional near Planck line. But this gives you a solid, robust, and completely generic proof as to how that happens. We have a geometry, and from that geometry we can prove. It tells you one more thing. It tells you when you go this n surface, n bulk, and all these calculations and push it as much as possible, it tells you that there is some kind of a minimum space-time degrees of freedom, which is like the basic quantum of information, which turns out to be, you take the minimum radius LP square, 2 dimension, so it is 4 pi LP square, that is where the 2-dimensional nature comes in. You divide that by LP square, you get 4 pi. Okay. Of course, this is not an integer, so when you are talking about quantum of information, you are just talking that this 4 pi is your quantum of information. You can divide this by 4 pi and say there is 1 unit of information, but this number comes out of this. Now comes the last bit. I told you that you have to get more than what you have thought about, and that happens in cosmological constant. It comes out as a relic of the pre-geometric space-time. So this gives you a completely different approach to cosmology. And in order to orient you towards this, let me tell you about a few things which is usually not stressed upon. The first thing which came up during discussion in one of the previous lectures is that the large scale universe defines a Lorentz frame. This is the frame in which cosmic micro background radiation is isotropic. I am not saying special theory is wrong or any such thing, everything will take care of itself, but it is true that the large scale structure of the space time does define a Lorentz frame for you. This is something very, very peculiar and not often talked about. If I take some quantum mechanical system and you let it evolve in time, it almost never becomes more and more classical. In some precise sense, I mean, you can use Wigner function or some other measure to call the classicality. But the universe is supposed to have done this. At very close to Planck time, the universe was supposed to be quantum mechanical. Why didn't you stay quantum mechanical? It can have an evolution by some functional Schrodinger equation. It can continue to be quantum mechanical today, but it evolved into classicality. This is another peculiar feature. Third, we see that the cosmic evolution also is evolving towards holographic equipartition. So let me spend a little bit of time on that in a minute. But the basic point is that we should not, what this teaches us is that we should not describe the cosmos as a particular solution to gravitational field equation. I have thrown in a reference for you to look at for more details, but roughly speaking what happens is the following. Again, if you think thermodynamically, it is very easy. Suppose I have a system which is described by thermodynamic equations, and you ask where that description breaks down. Of course, the first thing you think of is when you are talking close to the atomic and molecular size. When things are of the size of the mean free path of the system, you cannot use thermodynamic continuum description. You need at least kinetic theory, probably more. But there is another place where thermodynamic description breaks down, which is very so obvious that you don't think about it. Suppose you have some region of the fluid and you did something here, you exploded something here. Then it will take some time for the entire fluid to readjust to come into thermodynamic equilibrium. So this is an infrared large scale effect. At very small scales, it breaks down at mean free path, that is easy to understand. But you should also ask whether thermodynamic equilibrium has had time to set in. What is happening here is that as far as cosmology is concerned, it has not reached the thermodynamic equipartition we have been talking about. So, as a result of which at a very large scale, the equations of thermodynamic equipartition is not valid. The equations of thermodynamic equipartition is equivalent to Einstein's equation. There are corrections to it which you have to take into account. These are much beyond what we can detect observationally today, but there are some relics which is what we will come to. I will skip this because I wanted to give you some idea about cosmogenesis, but I do not have time for it. Now, let me come to this. So, if you take this thermodynamic paradigm and ask how do you describe the universe, the description is very beautiful. It is described by these two equations. First equation tells you is that the total energy inside a Hubble volume is equal to the surface heat density. We have seen this in several cases, T times S, T is h over 2 pi, S is area upon 4, and you have the standard definitions for bulk and surface, except that you throw in a sign. This sign can flip. So, you would like to have n bulk to be positive. So, you throw in a sign. Second equation, think of minus sign, that is nicer to think about, and that is what the current phase of the universe is. The volume of the universe changes because of n surface minus n bulk. There is not even a 3 pi by 4 or anything here. It is just LP square times. These two equations are, you can actually derive it from the 2 Friedmann equation. We wrote down 2 Friedmann equation, one with A dot square upon A square and the other with A double dot upon A. These are exactly those two equations. So, the universe has a very clean thermodynamic description, but what is going to happen is that these equations are equivalent to Einstein's equation, but there are going to be corrections. And we want to understand what these corrections are. We have some ideas on it, but it has not come to a stage where I can give a lecture like this about it. This also tells you that you can see quantum gravity in the sky at a very infraredish scale. How it comes up is the following. Suppose you think of the universe, the sphere out there, and you are here, and suppose you go up to an energy scale of 1 eV radially out. Then you are going back in time and you hit the time of CMBR. You go further back, you will get electroweak unification. So, suppose you can probe deeper and deeper. Right now, of course, any photon based observation is limited to this, but maybe if you do neutrinos, you can go up to this. But theoretically, in principle, information can come from even earlier. So, if you are looking deeper and deeper into the space to further and further reaches, you are looking at the universe at earlier and earlier times. It is as simple as that. Then you can probe gut scale, and at some stage you will see the quantum gravitational scale. This is Big Bang. But of course, we know Big Bang never happened. Quantum gravity has to correct it. And what it has corrected is written for you in the sky, but it is just that we cannot detect it observationally. What is going to happen is that this outside region is going to be like one phase, and this emergent inside phase where some kind of an equipartition has taken place is going to be a different phase. You are thinking of a pre-geometry to geometry transition somewhere here. So, this is the picture which you should have in your mind. That kind of cosmogenesis has to give you two numbers. One number is something which we have talked about for a long time. The other number is that it should also give you the fluctuations around this mean cosmological density, which usually is coming from inflation, but I have done away with inflation. So, this has to come from the primordial phase. Now, here it is, and it should also have a scale invariant spectrum. Here again, if you are innocent of inflation, you will, whatever I am going to say will make sense, but you know there are cosmologists around. So, let me spend a moment demystifying this called scale invariant. You will hear all kinds of things like, oh, inflation predicts scale invariance, it is a unique signature. It is all nonsense. So, let me explain to you what happens. In inflation, why do you get a scale invariant spectrum? It is an enormously simple reason. In the inflationary physics, there is a H inverse which is constant, and then it goes like this, and you will have a mode which crosses like this. This mode is just an oscillator of the field. You decompose the field into oscillators. Take any one oscillator. So, here is the mode, and it will be in the ground state somewhere here. It evolves, and when it is outside, the evolution gets frozen. That comes from the dynamics. And it is this frozen value which you are going to measure when it enters, and that is what your 10 to the minus 5a. What is more, the k cube times the fluctuations of the scalar field happens to be independent of k. That is called the scale invariant perturbation. The reason it comes out is enormously simple. If you write down the action for a scalar field, what you will have is a dt times from a root minus g, you will pick up a cube, and then you will have phi dot square etc., and then you will get a k square upon a square times the q k square. So, this a cube comes from geometry. This is like the mass of this mass of the harmonic oscillator, mass goes as a cube and the frequency goes as k by a. So, if you take a ground state of the oscillator, the sigma square of the ground state, which is the fluctuation, will go as 1 upon m omega, half m omega q square is the ground state. So, that will go as a cube times k by a. So, when the mode is somewhere here, it will just evolve adiabatically, and at this point it gets frozen. Where does it get frozen? It gets frozen at a point where the k by AC, which is the co-moving wavelength of proper wavelength of the scale inverted, matches with the Hubble radius, that is h inverse is equal to a by k. So, this is the moment at which it gets frozen. So, the sigma square gets frozen at that value, and that is what you are going to pick up here. So, what is that sigma square? It is AC cube and k by AC. K by AC is h, put that h here, and for AC cube you write k by h cube. So, h cube goes to the top and you get a k cube, and one h cancels out from this. K by AC is that h cubed upon h gives you h square. Therefore, k cube times sigma square is independent of scale. This did not require anything like inflation. There is a much general class of systems where this can come about. And this is, if you do not read any other reference I have cited, this is one reference you should read. The so called scale invariant spectrum also has a name, it is called Harrison-Seldowitz spectrum. And this is supposed to come from inflation, except that it was derived 1 decade before. And there is a very beautiful paper which I have checked with cosmology. So, this statement is true, it is very often cited and very rarely read. So, you should go and read it. And the title of that paper is telling. It says fluctuations at the threshold of classical cosmology, something making a transition from quantum cosmology to classical cosmology, how will the fluctuations evolve. And this gentleman showed with heuristic arguments that it will give you a scale invariant spectrum. So, in fact, in standard inflationary model you can get any spectrum you want, almost any spectrum you want, provided you are allowed to tinker with the initial quantum state. So, there is an assumption that the initial quantum state is some state called Bunch-Davies state, and that is how you get this result. What is a crucial test of inflation is something called running of the spectral index. I said sigma square k cubed is constant. That is not a completely true statement. There is a small weak dependence in this k, and that is being measured. And any model which you are throwing at this has to come up with this running, and that running is a non-trivial test, not just getting the 0th order scaling. Okay. So, that was just to give you an idea, and then finally let me tell you very briefly how this model predicts the numerical value of the cosmological constant. So, in order to do that, you want to study the amount of cosmic information and try to tie it up with a pre-geometric level of information, because information exists in quantum theory and classical theory and can provide a bridge. So, you start by the co-moving distance which a signal could have gone from A1 to A2, this is this integral, and you can compute this. And you ask, suppose you have an eternal observer, a guy who is willing to wait to get signals from all over, from the distant reaches of the universe. So, the eternal observer is going to look at it at very late time. So, I have put infinity here, and he is going to look at this expression from some epoch. Now, you want to know how this integral behaves. It is very elementary to show that this integral is infinite if nothing like cosmological constant is milling around, that is if rho plus 3p is always positive, you can show that this is infinite. So, if you wait long enough, you can see everything in the universe. But if there is a cosmological constant, this integral is finite. It is finite even from 0. So, you get a finite value for this. Therefore, you can link up information with the accessibility of information to cosmological constant. Let me try to give you diagrammatically what happened. This is the time axis, this is the logarithm of the expansion factor, these are length scales, all in co-moving scales. So, there is particular place I have drawn a line and said AQG. Before this, we do not know what is happening. This is the pre-geometric Corning gravitational phase. It made a transition to classical phase here, and I am going to assume originally it was radiation dominated, then it became matter dominated, then lambda dominated. I am just using what we know exists in the universe. Radiation exists, matter exists, lambda exists. Then you draw this co-moving Hubble scale. What I drew here is the proper Hubble scale. If you draw the co-moving Hubble scale, in the radiation dominated it goes linearly, and in lambda dominated it goes linearly in the opposite direction. In between, in the matter dominated it behaves differently, and then it turns around. This is the point at which lambda starts dominating the evolution. This is the behavior. Now you start talking about what does x infinity of A is. It turns out that it behaves like this. So there is a finite distance at any given A from which an eternal observer can get signals. And there is a cutoff here, because beyond that we do not know what is going on. So there is a band here of co-moving scales, and if you think of any scalar field or whatever whose perturbation, whose k we are going to take from, which is evolving like this, the co-moving scales of this are flowing in this direction. Then you can go and ask how many co-moving scales I can see, that is I can count how many modes are going to enter the Hubble radius between this cutoff point and here. This is dynamics, because this thing tells me there is a ceiling beyond which I cannot see. So I put that bound and then I count how many of them are there. So the counting is standard phase space, that is d3x d3p upon 2 pi h cross the whole cube, that gives you the number. You can do that counting, and the total number of modes which enter the Hubble radius in this phase actually has a expression which involve the co-moving Hubble scale at lambda and co-moving Hubble scale at that cutoff point. So this you can rewrite in terms of the parameters of the universe. This is the rho lambda, this is rho uq, we have met them yesterday. Then this is the scale at which that AQG occurs, that is the scale when which the transition from pre-geometric to geometric phase occurs. You can rewrite this equation, this logarithm becomes exponential in this form. And you can trade off that EQG to the amplitude of the perturbations coming from the pre-geometric phase, because we are counting modes. So you can play exactly the same game like that what I have told you, and you get a scale invariant perturbation with an amplitude, and you write everything in terms of that amplitude because it is measured quantity. Rho EQ is a measured quantity, and we know this. The rho lambda is related to this information content. This information content is essentially the number of modes which you have. So you get this formula with all these factors. First thing you notice is that if the information content is infinite, rho lambda is 0. That is true, because if the rho lambda is 0, that line goes just like this and infinite number of modes will enter. For those of you who can't immediately grasp, this line turned around because of cosmological constant, otherwise it will just go like this, and the modes which can enter all throughout is infinite. So that equation is verified here. So you have some factor here. But what is more, we have discovered that there is a quantum of information in the pre-geometric phase 4 pi, which is a good choice to put here, and once you put it, you get a number like this. This relates three things which everybody thought has absolutely no relation with each other. It relates rho lambda, rho EQ, and the amplitude of the fluctuation. Everything else is numerical factors. Now you can go and plug these in and see what happens. What happens is the following. It is normalized in such a way that you get rho EQ upon what is the measured quantity, and this is rho lambda upon rho lambda this thing, and you take the amplitude. All these three curves will go through a point. But of course in real observational astronomy there are error bars. So if you throw in an error bar, very charitable level of error bar, this will go in this band, this will go in this band, and you are somewhere inside this box. Now if you put the error bars and the amplitude, you still find this. Of course one fond hope is, if the universe later on turns out to be here, this model is ruled out at something like 0.5 sigma. It is not really something. I am not going to throw away the model if the universe happens to be here. Okay? But if the fact that it is inside this contour now is what is giving you faith in this theory. This was not designed to explain cosmological constants numerical value. You did not guess that there is going to be a 4 pi coming around and that 4 pi is going to mix up with this and a strange equation like this will come about. You can write this in a slightly more dramatic way. You take that equation in which I threw in 4 pi, but instead of that you keep that the 4 pi arbitrary and you write down IC in terms of all these quantities. Then the theory predicts that it is 4 pi. Okay. So, let us not be ambitious, let us not throw in 4 pi from quantum gravity. Let us go and ask what this is. We know rho lambda, we know rho eq, we know A and we know this constant, so plug it in. You will find that it is 4 pi to an accuracy of 1 part in 10 to the minus 3. And this 10 to the minus 3 comes from observational inaccuracy. So, you have a completely weird combination which no one could have guessed that arbitrarily with numbers like this, which gives you 4 pi to 1 part in 10 to the minus 3. And this is why we believe that there is a lot in this model. This is still speculative, one has to fix it better, you have to consider that pre-geometric to geometric transition, etc., etc. So, that is essentially my last slide, but let me just go over to summarize what we have done. We started with 3 clues. The thermality of the horizon, let me just put all of them there and then talk about it. First is that it gives you a new level of observer dependence, but it gives you covariance without covariance because of the fact that it should hold for all observers. Second, you can use that to count the atoms of space-time. It gives you a picture where macroscopic gravity is like continuum field dynamics, and the actual Einstein's equation describe heating and cooling of space-time. And you can write down the equations to the universe in this language and you anticipate corrections to it. So, it is not exactly going to follow Einstein's equation. Then you take the second clue, which is the cosmological constant, that gave you a philosophy that you should respect this symmetry, and this tells you that immediately gravity is sourced by heat density and not by energy density, that is a paradigm shift. Once you want this invariance in any local action principle or an extremum principle, metric cannot be the dynamical variables, you must be using some other principle to get the result, and you are essentially going to maximize log of omega g into omega e. And this lambda is a integration constant and its value has to be fixed by some other principle. Finally, we had the 0 point length as the third clue. This tells you that you should first of all work with sigma square rather than with metric. Sigma square is a more fundamental quantity and that you get modified to incorporate the 0 point length, which allows you in a very natural way to obtain the degrees of freedom of omega g as the area associated with an event. It did not vanish while the volume vanished. Then from the it also tells you what is your pi for the atoms of space time. It came out of the analysis. These are the null vectors, and it told you that the quanta of information is 4 pi. When you combine it, you get the numerical value of lambda. So, this is the sort of take home message that you started with 3 points where gravity and quantum theory had contacts and conflict. If you use them in particular way, you end up getting a particular a perspective on gravity which is different from the conventional perspective, and that gives you lot more insight. But of course, there is lot more work to be done. You have to finally get a microscopic picture. We have only gone up to mesoscopic. I will stop there. Question?